turn off a set of lights here. Other bad thing about the setup of this room is that I'm over here and the projector screen's over there. So I'm going to try to minimize the amount of time you spend turning around as much as possible. Most of the time you can focus up there and I'll just be kind of a narrator. So today we'll talk about Chapter 1. And at 12:05 I will give you a 10-minute break because I realize that 2.5 hours is long. And today we're probably going to go over the hour and 15 minutes in the first half, and then we'll still have time for playing around on the computers after that, but I want to get through Chapter 1 today. I like the way this book has its first chapter. It pretty much throws everything at you in a very small amount of detail, so that in the later chapters we can go through and talk about each individual topic in greater detail. The first section talks about computers and what computers are. Computers are both hardware and software, so we had a couple computer engineers in here. That's very much the hardware end. Computer science has now gone very much the software end, and ironically, a lot of computer engineers are now writing hardware in software. So software is important. This class focuses mostly on software. This little discussion here is really the only coverage of hardware that we'll talk about. Computers, sorry, I guess I won't be typing quite yet, but talking first. Computers, in essence, consist of input over here, output over here, and then something in the middle that takes input and turns it into output. It's a very simplistic view of computers, but it's also very accurate. Computers are not anything complicated. They have these cool UIs and stuff, but they're really nothing complicated. Computers really mainly just add and subtract numbers, and in fact that's mostly adding numbers because you represent a number as negative, add it, and there you have subtraction. So computers add numbers. That's all they do. But in order to add those numbers, they need a few components. One component is the processor, also known as CPU, Central Processing Unit. This is the thing that actually adds the numbers. When you say add two numbers together, this actually adds those two numbers together. You also have memory, also known as RAM. Stands for Random Access Memory. That's where all these numbers are stored. And we'll talk a little bit later about characters and numbers and how they're interrelated. But characters, letters, are also numbers. Everything's a number in a computer. It's all stored in memory. Goes through the processor and turns input into output. And this is all very general purpose. And this wasn't until 40 years ago or so, dawn of time as far as computers are concerned, but only 40 years ago, general purpose computers came about. Before that, you had punched cards, you had a computer that was built specifically for one purpose. In fact, the history of the term computer originated during World War II and it referred to people, usually women because the men were off in Europe fighting, that sat and calculated trajectories for ballistic missiles. Computed these tables of angles and whatnot for these projectiles, hence computer, someone who computed. Then you have the electronic computer, and then electronic computers became so prevalent that we just dropped the electronic. And now the only computers that we think of are electronic computers. Once we have the general purpose computer, which in theory can compute any problem that is computable, it's a tautology. Don't worry about it. You'll get to it in automata. And you'll talk about what it means to be computable. There is a certain class of problems that can be solved with computers, and other classes of problems which not that can't be solved by computers. We don't know if they can be solved by computers. So these general purpose computers can solve those problems. In order to solve those problems, we need some instructions for how the computer is going to operate on its input and generate its output, and what it's actually going to do to solve the problem. And then we get the notion of program. So, in memory, we have numbers and we also have this program. Memory is organized by address, basically a number that represents where in memory something is. Computers can only deal with numbers, so it uses numbers to identify where the numbers are. It's organized by bytes. A byte is a series of 8 bits, which is simply a state, on or off. With 8 bits, there are 256 possible combinations, and they can be enumerated starting with the first one as 0, which is all offs, all zeros, and going all the way up to 255, which is every bit is on, every bit is a 1. And binary is a way that we can express numbers as well, not just computers. We had to define some way for the computer to express these digits. But you'll learn how to convert decimal to binary somewhere else, hopefully. It's not that hard. It's pretty straightforward. I think you can probably pull up the Wikipedia page and it'll explain how to do it. Why did they choose binary bits that only had an on state and an off state? The fact of the matter is that it's very easy to determine whether something has voltage or doesn't have voltage. Either there's an electrical current or there isn't. There's not much ambiguity there. Any other number of states, you can't really figure it out. If you had high voltage, no voltage, and some voltage in the middle, it would be very difficult to determine where that is, because power fluctuations, electrical storms can all mess with that stuff. They tried making base 10 computers with 10 different states for each digit. That didn't work very well. They abandoned that very quickly. Vacuum tubes worked much better. So now we have a general purpose computer, we have programs. In the beginning, computers were programmed by unplugging wires and plugging them in somewhere else. That's very inefficient. Then we went to punch cards, which was each card contained a single instruction that was a single operation for the computer to do. And it was a bunch of numbers. That's not that fun to write and even less fun to debug. Not to mention that when you get your deck of cards printed, give it to the computer operator, because at this time computers were massive things, bigger than this room, and there was hopefully one person on site that knew how to operate it, and maybe a couple others that vaguely knew how to watch them. But you as a programmer had absolutely no idea how this computer worked, so you'd give the operator a deck of cards. They would eventually run your program through the computer, one program at a time. If you were 13th in line, you had to wait for 13 other programs to go. And 2 weeks later, you find out that your program had an infinite loop and never ended, and the operator had to cut off the job so someone else's program can run. And now you have to look through your deck of cards and figure out where the bug was. And God forbid you drop the deck of cards. luckily, they had sequence numbers on them, so that wasn't too big a deal. But still, you had to put them back into order and hopefully get the order right. So after that, two advancements happened. One, we moved away from punch cards and went to stored programs. We're racing ahead a little bit, but something like floppy disks. And we went to a language where we could type in something that looked like English, but still type in terms of instructions that the computer understood. And then there was a program which was called an assembler, which took this program that we wrote in something that looked vaguely like English and turned it into machine code that the machine could understand. And there was a one-to-one correlation between a line of assembly code and a single instruction of machine code. So if I wanted to add two numbers, I would say add this number and that number, and it would turn into a binary representation of that, a machine language representation of that. Still a pain to write large programs because computers operate at a very, very atomic level, single operation at a time. Even multiplication is difficult for some computers. Fast forwarding a little bit more, we get languages like the predecessor of C++, C. This is around 1969. To three computer nerds at Bell Labs, they want to play a computer game on a system that's just sitting around. So they write this programming language called C, and this is a higher level language. The book calls it a high level, very high level language. The book makes a distinction between high level languages and low level languages. It calls assembly a low level language and everything else a high level language. C is really somewhere in between, because you still have to think in terms of memory and where your program and data is being stored in memory, but you have constructs that flow a little bit more like you would speak in English. If some condition, do something else. Otherwise, do something else. And we needed programs or some method of taking this C program and turning it into assembly language so that could be assembled into machine code. So now we have programs called compilers, which compile the source code, which in this case is written in C, turn it into assembly code, and then the assembler takes it the rest of the way. Fast forward several decades to Sun Microsystems in 1995. Someone wants to prove that you can write a program in a language, compile it to something lower level, and then run it on any computer, regardless of operating system, platform, all that nonsense. You can run it in your car now. Most basic phones, non-smartphones, use Java. Android uses Java. Java is all over the place. But the original idea was that you compile it once, distribute it, and then any computer that has a Java virtual machine on it, which knows how to understand this compiled Java code, can run this program. So that's kind of like an emulator, yes. It's a little bit lower level than that because emulators are usually written for archaic processors that are no longer around, so you can run, for example, I'll run Gizmos and Gadgets, a very old DOS game from when I was in middle school, on my current Mac, which is multiple times faster than that and doesn't even speak the same machine language. How did I get off on that? Right, Java Virtual Machine. So it's basically this simulated computer that runs as a program on your actual computer, and you can write these programs that run on top of that. So we'll write programs, compile them, and run them on Java Virtual Machines. And in theory, you write them on these computers in the lab, and I should be able to run them. If you compile them here, I should be able to run them on my Mac. Different versions of Java make that a little bit harder than it sounds, but it is possible. Speaking of computers, you're welcome to use the computers in the lab. It's nice of the university to provide these computers. However, you'll notice I'm not using this computer. I avoid Windows like the plague. I like Mac OS X. If you don't want to use the computers in the lab, you're more than welcome to bring a laptop to class. If you can find a way to write Java on an iPad, go right ahead. There's nothing. I'm not going to require that it's written on these computers because it's write once, compile once, run anywhere. And especially since you'll be submitting source code, I will be able to compile it as well. So someone mentioned websites. I think it was you. One of Java's first branches of popularity was in the form of applets, interactive pieces of websites. That's kind of been superseded now by Flash and then Silverlight and DirectX stuff, which has also been superseded by Silverlight, and now finally by HTML5, something that doesn't steal your processor when you try to run it. But Java did provide a very interactive, simple way to make interactive content on a website. Since then, it's grown into being used for desktop programs. My company had a program that was written in Java. We recently dropped Java because Apple and Oracle can't figure out what version they're going to use and whether or not they're going to support it anymore. But Java is very convenient for writing one program that can run on both Windows and OS X. That's why we used it. I mentioned Java is also used on Android. It is the go-to language for Android apps. It's used for web programming now, and enterprise-level web programming. There are several frameworks that make that fairly straightforward. It's pretty much the silent competitor to Microsoft's .NET platform. So with that, let's look at what page? Page 15. And we'll actually write a Java program. First things first. In this class, so the book mentions the command line Java tools. You can use those if you really want to. They're not the easiest thing in the world to use. I prefer Dr. Java, and I think it's much easier to use, especially for learning Java. You can focus on learning the language instead of learning how to compile and run the programs. Dr. Java handles that for you, so you can focus on how Java works. If you search for Dr. Java, this site, drjava.sourceforge.net, is the first Google result. If you go down here to current stable release, and for you guys using Windows, click download Windows app. And on mine, I clicked download Mac OS X app. You can download Dr. Java. It is not an installer. And if SourceForge comes up with something that looks like a form that looks like you have to register in order to download, you don't have to. Click the link and you'll be able to download. It does not come as an installer. It is a standalone program, which makes it very nice to put on flash drives. You can stick it on a flash drive, carry it to class, carry it down to the computer to the library. You don't have to worry about finding a computer with Dr. Java installed on it. because if you're on UCCS campus, you'll be looking for a very long time. It's not installed on any computer on campus.
Is it a PNG file?
The Mac is it's a good question. The Mac version is, it's either a zip or a DMG. It is, it's a tar.gz. Mac can open tar.gz files by default. And inside, I believe it's just an app bundle. So you can drag it to applications and run it from there. The Windows version, it's just an exe. So you can put it wherever you want. Put it on your desktop. Put it on a flash drive. You can put it on your student drive, whatever it's called, your Z, H, whatever. I don't recommend saving anything on your desktop on these computers because for some reason the desktop isn't linked with your student profile. So it's local to that machine. I recommend saving anything you create in this room to either your student drive or to a flash drive. So once you're welcome to follow along with me as I type. Not required. You can also follow along later on when you watch the video. This is also listing 1.1 on page 15. If you want to follow along, you should download it. If you don't want to follow along, you don't have to. If you download it, I recommend saving it somewhere that you know where to find it, so that you can use it again next class. This book does not have line numbers next to its listings, but I will try to keep the spacing as close to looking like the book as possible. And most of this, well, all of this should look foreign at the moment. Most of this probably doesn't make sense. We'll make some sense of some of it after I finish typing everything. And some of it will be, just trust me, you'll need this in Java programs. And then later on we'll learn what it actually means. Yes. So I have made a couple customizations to the layout of Dr. Java. It doesn't, by default, show line numbers. By default, the font is a little smaller, but it does automatically provide what's called syntax highlighting for you. That means that stuff in double quotes shows up in one color. It's difficult to see on the projector, but keywords show up in blue. This shows up in a darker blue. That there's special importance associated with that stuff that I'll talk about in a minute and later on in the semester. And everything else shows up in black. And also it highlights what are called blocks. These curly braces begin and end a block. So when you type a curly brace, it shows you what the extent of the block is, what curly brace it matches with. So if I were to go up to the other one, it would show everything green so that I could see. It just makes it easier to figure out where I am and what I'm doing and hopefully reduce typing mistakes. There's also a typo in this listing. On the very last line that is not a curly brace, that one, in the print 1N should not be a 1, it should be an L. After I found that, I went looking for errata for this book. I can't find any, so as we find mistakes, we'll make a note of them.
So is that for both N1s or just the bottom one?
The 1N. It says print 1N. That should be print LN, not print 1N.
Okay.
I'm not a touch typer. Thank you. Oh, it's a 1 in both of those last two lines. So both places should be an L. When you're done typing in the code, I recommend saving the file. You need to save the file before you can compile and run it. And Java has some very specific naming conventions that they're more than conventions. They're pretty much forced. Whatever you have in this position in the file, next to public class, so in this case it's first program with the F capitalized and the P capitalized, that is the name of the file. That needs to be the name of the file. I have no choice in that. I have to name it firstprogram.java with the same capitalization. And it's a convention that what are called Java classes. We'll talk about classes later, but this is a Java class. They are named with something called title case. That means the first letter of every single word is capitalized, and then all the words are smashed together. No underscores, no spaces, just word after word after word, the first letter of each word capitalized. So at this point I can compile. And eventually there we go. Run it. And we first see it prints out, hello out there, I will add 2 numbers for you, enter 2 whole numbers on a line, which is these 3 strings, sequences of characters between double quotes. And Dr. Java makes it very obvious that it's asking for input. I'll type in 7 and 8 with space in between. The sum of those two numbers is 15. So just from writing this program and running it, we can figure out a couple of different things. First of all, this is a structure of a Java program that works. Secondly, this system.out.println seems to print stuff to the screen. And it does exactly that. It prints whatever the argument is, whatever you put in parentheses. In this case, hello out there, then I will add 2 numbers for you, then enter 2 whole numbers on a line. And it prints out that, followed by a new line. So it prints out whatever I give to it in parentheses on a line by itself. So the next thing I print out is on the next line. After that, I'll start from the top and start explaining what some stuff does. Line number. Yes.
When I was reading over the first chapter, I was confused about objects and methods. Is that something that I'm going to have concrete, or?
We won't really talk about objects and methods until we'll talk about them philosophically, theoretically, after the break.
Okay.
But we will talk about their implementation in Java in, if I can find the table of contents, here we go. Chapter 5, defining classes and methods. So don't worry if objects and methods don't really make sense right now. As I mentioned before, first program is a class, and that's not too much of a stretch. We say class and then some name. The name is a class. So if you see class in the book, that's what it's referring to. We won't really talk about what a class is or what it means to have a class until later on. Chapter 5. Method, we won't really talk about what a method is, how a method works right now. But this main thing is a method. It's referred to as the main method because it is the entry point for a Java program. That's important. The entry point for a Java program is public static void main string args. Good thing to remember. Hint will be on exam. That sequence of stuff, public static void main string args, exactly like that, is the only entry point for a Java program. Java looks for a method that looks like that, and that's where it starts running your Java program.
The argument within the parentheses after the main statement can be anything, or does it have to?
It has to be that exactly. String, open square bracket, close square bracket, space args. We won't learn about any of that quite yet. We won't learn what public means, static, void, string, square brackets, or args. Don't worry about that. The important part is that whole construct. Everything in between the curly braces that follow public static void main string args is, for now, our entire program. And this falls under the category of what's called sequence. Any machine that can solve the class of problems that a computer can solve needs to be able to perform sequence selection and iteration. Sequence is the ability to execute one instruction after the other. That's what we're dealing with now. Selection is the ability to execute a series of instructions based on some condition. We'll learn about that in a couple days. And iteration is the ability to execute a series of instructions multiple times, subject to some condition. And we'll talk about that a couple days after that. So, going through line by line. Line 1, Java provides some stuff. And there are two classes, I can't use the word class, two ways that Java provides things to your program. There are some things that your program automatically has. Basically, everything that is necessary for the Java language to exist already is in your program. So things like system. Most Java programs somehow use the system. So system is automatically provided to your Java program. This int thing, which we won't quite learn about what it is quite yet, this int is provided to your program automatically. Scanner, on the other hand, is not automatically provided to your Java program. So if we're going to use it, we have to specifically say, I know this exists and I want to use it. This is part of the Java's framework. So the framework is a set of code that your program can use that someone else has already written. That's just there. This import statement says, I want to use java.util.scanner. This framework is organized into a hierarchy. So classes and objects that are in this this framework are grouped according to function. So Java indicates that it's part of the Java framework. Util means this is the set of utility classes, and then scanner is the actual class name. And there's actually some very serious documentation. Known as the API documentation. API stands for Application Programming Interface. And there's a link from this to this from the course website. This is every technical detail you could possibly want to know about the Java framework, which means every technical detail that you really don't want to see at this point. But it's there. This is documentation of everything that's in the Java framework, and as we start using more and more of Java, it will become useful. So that can go away. So let's talk about line 8, system.out.println. System is a class representing the system. Everything that the system represents that Java might need to use. It has two pieces that are very useful for our programs right now, in and out. And remember I talked about how a computer takes input and gives output and does some processing in the middle? In represents the input, out represents the output. Or more realistically, the mechanism for getting the input and the mechanism for giving the output. And println is, it's a method that says print this stuff and it's part of out. So it prints it to output. On line 15, the in property of system is used. And that's used to receive keyboard input. Until Java 1.5, so 7 or 8 years ago, Java had no standardized way for getting input from the keyboard. I didn't design the language, I don't know why that is. At about Java 1.5, they decided, hey, we should have a standardized way to get input from the keyboard. And they built this scanner thing. Scanner is pretty much ubiquitously used to get keyboard input, and it's a wrapper around system.in. And that's what's specified in the second half of the line. So we say, give me a scanner that uses system.in, and then I can get ints from it, whatever an int is. We'll learn more about ints, I think next class, when we talk about variables and data storage. I'm sure I could go on for hours about this program, but it's 12:05, so I'll let you have a 10-minute break. Wrap your heads around it. You want to ask your question first?
During the break is fine, yeah.
Okay. So 10 minutes, and then I'll talk about section 1.3.
I'm sorry, I asked myself when I know it's rude. My friends